Okay, everybody, on this particular lesson, we're going to learn more about osmosis, which is really just a special case of diffusion with water. And it has some unique properties because the water is the universal solvent. I should say universal, but it is a very excellent solvent. So, osmosis, by definition, is the net movement of water molecules across a semi-permeable membrane. So, water molecules across a semi-permeable membrane, like a cell membrane, towards the area of higher concentration of solute. So, let's take a second here and let's define here solution, solute, and solvent. So, we have a solution, which is a mixture um, of a liquid, the solvent, that would be water, and some particles that are dissolved within it, the solute. So these little purple positive charges and these orange negative charged ions here represent the solutes. So this represents an area of high solute concentration. And this represents an area of low solute concentration. Now, if we think of it in pure definition of diffusion, this still is diffusion because we're talking about the movement of water molecules from high water concentration to lower water concentration over here. But if you think of it, it's always going toward the solute, the dissolved substances. That seems to clear up a lot of misconceptions. Okay, just like diffusion, there are things that affect the rate, and that is the higher the temperature, the faster the rate of osmosis, just like the faster the rate of diffusion. If there is a bigger difference, the second one here, if there's a bigger difference in the concentration gradients, like very high water concentration, low solute concentration, high solute concentration, low water concentration, the bigger the difference between those two, the faster the rate of osmosis and diffusion. And then how permeable this membrane is to letting these molecules through, these water molecules. The more permeable, the faster the rate, obviously. The less permeable, the slower the rate. So if you notice this, there's these two things here. You got a hypertonic and a hypotonic. So on the hypertonic, there are fewer free water molecules. Many of these water molecules are in what are called a hydration shell. So that is that they're surrounding this solute. And remember that the hydrogens on water tend to be slightly positive, and they're attracted to this negative ion. So these like four molecules here are kind of like taken up in this hydration shell. Just like on this side, these four molecules of water are taken up on this hydration cell as the slightly negative oxygen is attracted to this positive ion. So there's fewer of these free water molecules, ones that are not in these hydration shells, than there is over here. Hypotonic now is where there is a lot fewer of these free water molecules. I'm sorry, there's more free water molecules and fewer that are stuck in these hydration shells. Another way to think about this, hyper, let's think about the solutes. Hyper. When you think of something hyper, they're like more energy. They got all this energy. There's more, 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 more. Okay, so there's more solutes on this side, more solutes. And hypo is the opposite. So, okay, isotonic is where the two sides are equal. So we look at this top side versus this bottom side. The two sides are equal in their concentration of solutes or soluble molecules. Reverse osmosis is a special kind of like property where they actually just use a lot of force and they push these molecules, these water molecules, from a hypertonic into a hypotonic solution. Okay, now osmosis in cells. Let's take a look at this particular situation. So we have osmosis taking place across a cell membrane. A lot of times what we have are these proteins called an aquaporin, which are channels which allow water to go through. They allow water to go much more quickly than they do just simply across the membrane. And so what effect does this have on cells? So in our first case down here, you've got an animal cell that's in an isotonic solution. Remember, isotonic means the same concentration on both sides. So there's an equal amount of water coming in as going out. And so really the water stays, the cell stays the same size. The second case here, an animal cell in hypertonic solution. Remember, hypertonic means that there's a greater concentration of solutes. So water goes towards the solutes. There's a greater concentration out here. So the water is going to move out. Water moves out of the cell. Hypertonic, the water is going to flow in because there's a higher concentration of solutes in the cell, so the water flows in. So let's go back to this case. What happens to this cell? As the water leaves, it shrivels. So it shrinks down, shrivels up. On this side, though, this is a deadly solution for cells, for animal cells, I should say, because the water goes in and it's like overfilling of a water balloon, and eventually it will pop. In plant cells, there's a special difference in that they have a cell wall around them. The cell wall kind of keeps its shape and is pretty firm. Isotonic solution, though, same amount of water is going in and out. Hypertonic, this is actually deadly for plant cells because normally you have this cell membrane. You can see these little bubbles forming here. This cell membrane is right up against it. But as the water moves to the side that has more solutes, this cell membrane starts pulling away from it. This is called plasmolysis. Plasmolysis when this happens to a plant cell. It's deadly to a plant cell. And in hypotonic, the water goes rushing in. And you remember when we talk about the animal cell over here, this was deadly. It caused the cell to explode. Well, plant cells, it just causes it to swell and become what we call turgid. Has a lot of pressure, but it does not burst because of that cell wall.